After we talk about how to use the BFS or DFS to iterate through the graph and find all the possible routes, now we can moving forward to see how to find the shortest route and the cheapest route. And also we will introduce the Dijkstra algorithm. The first thing about the shortest route, when we try to find a shortest route, of course, the first thing we need to know where we start. So we'll have the original node. Then where we will go. So we will select another node as the destination. So from the original node to the destination node, there are multiple possible routes, but we will find the minimum number of the step. So on this situation, when we consider for the shortest route, we don't think about all the link, they have the length. Instead, we only consider all the link, they have the same cost. So this one we call is unweighted edges. So from here, we will start learning how to find the shortest route. So then the next one, when we have each link, they cost differently. So this cost can be distance, can be the fare, your ticket fare, or it can be your mileage. So they have many different costs. So then after we consider the cost, then we will find the cheapest route. But here our shortest route, just like we say, the first thing you need to find, you have the original node to the destination node. And all we consider all the link, they have no weight. That means they are all considered is one. So then our shortest route algorithm is we need to keep track of the shortest path to each node. And we should stop once we find the end node. So this one is, what does that mean for these two steps? That means, for example, we use the BFS search algorithm. We will start from our original node. So we spread out to find all our neighbor. Since we will start find our neighbor's neighbor, so that's why they will spread out. Once we find the end node, we right away know this one is the shortest route. Why? We see here. Again, we come to the graph. So you will see here, we just say, for example, we want to find the shortest route from San Francisco to Chicago. So then you will see, actually, we will start from San Francisco, is the original node. So then we see all their neighbor. So then you see your first level neighbor. If you have the first level neighbor, you just right away find the Chicago, then you finish. Because we know if you finish the first level neighbor, right? So you see we go to the Denver. Denver possibly will also go to have another link to go to Chicago. But once we do that, you see we need to have one link, two link. So that's why definitely later on we find the destination, they will be not the shortest one. Because we will start from our original node. We go one level neighbor. Then after you finish all the first level neighbor, if we don't find the end node, we just continue from all the first level neighbor to go to spread out to using the second level neighbor. So that's why you see every time if you find the destination node, you know that will be the shortest route. Or let me show you from this graph before when I wrote on the whiteboard. You can see here we have the star node, right? So your star node, you see, you just focus on your neighbor. So you have all the level 1 neighbor. If from the level 1 neighbor, I didn't find the end node, then I just continue from this level 1 neighbor to spread out to looking for the level 1 neighbor's neighbor. So that's why you see you spread out, spread out. So then this one spread out, spread out, spread out. So then if after you spread out from your level 2 neighbor, you find the end node, then we find the shortest route. So then you will see from here, they will do 1 and 2. So even later on, they find the end node. Possibly end node will find out for you continue to spread out. But then actually we don't really care because they will be 1, 2, 3. They need 3 more steps. So so for example, we just say this one because there's 1 step, 2 step. So this one will be the shortest route from the start node to the end node. So that's why you see here, if I want to print the shortest route, I need to know where's the start point and where they go and how they link to the end node. So that's why here for the node struct information, we need to add more information. So that's why here you will see our node struct now, we need to add more. So we still have our city name. We still have the is visited or not, because that's important, right? If that visited, I don't need to visit again. So we still have the neighbor in the list using the index. But now we need to add 2 more attributes. The first attribute is a pref. So this pref means when I start building the route, which node is my previous node? So this one will be the integer to note which node is the previous node in the route. Then the second is the cost. But this cost actually is so far the total cost. So for example, you see from here, when I have the start, when I go to the level 1, 2, on the level 1 neighbor, you have 1, 2, 3. So then you will see their cost to come to this point will be 1. So then again, you see when we going out to find the level 2 neighbor, so then their cost also will be added by 1. So that's the cost we mean here. So the cost, that means when we start building the route, so what is the cost from the start node to this node? So that's our new node struct, right? So continue, what kind of algorithm we should use? So that's why we go back to see this one. Don't you feel this one is the same as we talked about before, is the BFS search? I spread out level by level. So then I have first level, I have the second level. So so here we will still have a to-do queue. So this to-do queue, the same thing is you have start from your start node. So then you mark you are visited. So you push to your to-do queue. So as long as your to-do queue is not empty, we need to consider to do our recursion step. We will pop the node from the to-do queue. So then we will visit that pop out node, the older neighbor, one by one. So then we will see if that neighbor is not visited. So then we need to update some information. So that's why you will see here, we're still using the to-do container actually is the queue. So that's why we can do our recursive step for that. So now you can see here, that's our algorithm. So this algorithm actually, like we say, we are looking for the shortest route, but this one actually is still we using the BFS algorithm for that. So that's why later you will see you still have a queue for the to-do. So then you will still have your recursion, but we just need to have more information we need to update. So the first one we see the initialization. Remember before we start, right? Before when we just do the BFS search to list all the possible routes, we mark all the node is not visited. But now since we have more information, because our new node become what? Our new node, besides we have the is visited, and we need to set as a false for the for the initialization. So then we have 2 more attributes we need to update. So here the cost, What do you think the default value? Right, 0. So how about the proof? The proof actually we cannot do 0 because 0 actually is the index as well. So that's why we need to make the proof equal to -1. The reason is because your database vector, the index start from 0. Right, so that's why you will see here, your recursive step, they kind of similar. So when we do before we start push any node to our queue, so then you need to have initialization. So your initialization, you need to update all the data from the database. So you need to mark the is visited equal to false. So the cost equal to 0. Then the proof equal to -1. So then of course in this function we still need to get the start node index. Then we need to have the database path. Of course now we need to add the new one. That means we need to have the end node, the index as well. So then afterward, right, so you still create a queue as a to-do list. So then the first thing when we start, we make the start node mark as a visited. So we push it to our to-do queue, right? So that's a to-do queue. So then remember here is our recursive step. While the to-do list is not empty. So that's why you see here is our recursion step. So as long as the to-do list is not empty, okay, so then you will have pop the node. So we will have this node is the node under consideration. So then you will visit, you're still using the iterator to iterate through this considerate node neighbor. Did you remember, right? We say if the neighbor being visited, then we just continue, we skip this node. Otherwise, before we just say we push the neighbor's index into the to-do list, right? So then we mark the neighbor as the list, as visited. But now because we need to find the shortest route, so these two actually is adding from the BFS search algorithm. We need to update the neighbor's cost equal to the considerate node cost plus 1. So then we set the neighbor previous to the index of the node under the consideration. So that's update the route info for all the neighbor node. So then afterward again, before we just finish, we go back to the while loop, right? But now remember, we will end if this node, the neighbor we are visited, if they are the end node. So that's why here, if the neighbor node is the end node of the NCT, yeah, actually you can just either exit from this while loop or you need to empty all the to-do list. But anyway, just mean you need to try to leave the while loop, then we finish. Because once the first one we find out the end node, we just exit. So after you exit from this while loop, right, then we need to build up our route. Right, so that's the proof from. So actually you need to build up, before we build up the queue, because we don't worry about the order. But here, when we want to return from our shortest route, actually we need to return a stack. Why the stack? Because now you know you need to have your end node first. Then from the end node, you have the end node proof value. So then you push to the stack, start from the end node. Then you find the proof. Once your proof reach the star, then your stack being established. So that's why you return the stack of your shortest route. So make sure you check the pseudocode to see if that's the BFS algorithm to find the shortest route is understandable for you. So you can pause anytime to check is that initialization update or how to handle the loop is the correct. So then we will moving forward to our source file. So download the BFS shortest.cpp file. So then here you will see, right, our node struct we change. So then focus on the BFS shortest function. So you see we passing the original node, end node, and the database. And we will return a stack. So that's contain the order for the shortest route. So this video will finish soon.